Hello and welcome to our week 5 preview for Chem 106 lab. The subject of both of the labs this week is all about rate laws. That is that part of kinetics where we look at how fast does a reaction go and how does that reaction speed relate to the concentrations of the substances inside of there. So before we get into the specifics regarding the pre-labs for this week, let's take a look at just kind of what a rate law is in general and how that information might be useful to us from a practical standpoint. So here we go. So in general, a rate law is a mathematical indication of the effect that a concentration of one of your reacting species has on the speed of the chemical reaction itself. So when we investigate kinetics, kinetics looks at the rate at which one reactant disappears or another product appears. A rate law helps us to determine how does that speed get changed based upon how much stuff is there. And in a lot of cases, there is a definitive relationship between the concentration of the substance and the speed at which the reaction runs. Now, there are two primary ways that we can look at these overall rate laws. One is called the method of initial rates, and this is more or less what you're going to be doing in the peroxide lab this week. And then there's the integrated rate law, where we take concentration data over time and we look at that data and we analyze those data. And that's going to be the subject of the food dye lab that you'll be doing virtually this week. And actually, you'll see this one again the following week as we get prepared for the crystal violet dye lab. So let's look at each one of these kind of individually. But before we do, let's kind of get into the basics and fundamentals of what a rate law is. In a rate law, we are looking at, for this general equation, A is reacting with B to make C and D. Each of those reactants has a coefficient associated with it. And the rate of reaction is equal to K, the rate constant, multiplied by the concentration of A, the initial concentration of A, mind you, raised to the power M. M is something called the reaction order for reactant A, and multiplied again by the initial concentration of B raised to the value of N, the order of reaction for reactant B. Now, these reaction orders are usually small integer numbers. And by small integer numbers, we usually mean they are 0, 1, or 2. Now, in more sophisticated kinds of reactions, fractional orders are possible, negative orders are possible. In fact, we call those inhibitors. But for the most part, reaction orders are going to fall into one of these three categories. It's either going to be 0 order, first order, or second order. And the relationship of these is going to have an impact on the rate. So obviously you can see that if I have something that is 0 order, raising that value to the 0th power means that A is going to have no impact on the rate at all. Whereas if I had a 2 here, squaring the concentration is going to have a much more significant impact on the rate than if I had only just first order reactant there. Now notice also these numbers, M and N, have absolutely nothing to do with A and B. A is not the same as M. B is not the same as N. This is important to note because it is often confused, because there are occasions where the stoichiometric coefficient and the order of reaction are the same. Those are purely coincidental. Reaction rate, reaction order has nothing to do with stoichiometry. Absolutely nothing. So what about these reaction orders? Well, their overall purpose is to give us some insight onto how does the concentration of that particular reactant directly impact the rate at which the reactant runs. The higher the order is, the faster the reaction will run. And so if we start with zero order reactants, that is 0th order, basically what we can say in any of these cases is that regardless of what happens to that concentration of the reactant, it has no impact on the rate of reaction. So I can double it, I can triple it, I can cut it in half, other than affecting potentially the yield of the reaction, it is not going to change the rate of reaction. First order reactants, these are where M is equal to 1. These have a linear relationship with rate. So when the reactant concentration doubles, the reaction rate doubles. When it triples, the reaction rate triples. If it's cut in half, it cuts in half as well. For second order reactants, N is equal to 2, we have an exponential relationship with rate. So if our reaction concentration doubles, the rate doubles, quadruples. If our reaction rate triples, then it triples, 3 to the second. It goes up by a factor of 9. We can determine the overall order of reaction by simply taking all of the sums of all of the orders for a given rate law. So the overall order of reaction is M plus N plus O plus P plus however many components factor into the rate law. And usually speaking, there are not more than maybe 3, maybe 4. Most of the time, it's 1, 2, 3 kinds of components that are directly related to the reaction itself. Again, it's important to note that there is no correlation between the stoichiometric coefficients and the rates and the rate laws. So take these for example. The decomposition of dinitrogen trioxide into nitrogen dioxide and oxygen. The stoichiometric coefficient for the dinitrogen trioxide is 2, yet it is a first order reactant. Doubling the concentration of the dinitrogen trioxide only doubles the reaction rate. It does not quadruple it. The second one's an example of kind of a weird setting where I've got chloroform reacting with chlorine to make carbon tetrachloride and hydrochloric acid. This substitution reaction gives us first order in chloroform, but not first order in chlorine. And chlorine is actually a half order. It's one of those rare fractional orders that I was talking about earlier. Hydrogen reacts with iodine to make hydrogen iodide. And in that case, both are first order, and that's perfectly fine. So it is possible that you can have the stoichiometry match up with the rate law. But again, that is coincidental. It is not a rule. So important thing to remember as we're kind of phrasing this out. Balancing the equation does not give you the rate law. Balancing the equation just makes sure that it adheres to the law of conservation of mass. Now, let's talk about the method of initial rates. The method of initial rates, and again, you will see this in the decomposition of hydrogen peroxide lab that you're going to do in lab in person this week. This is a method that is used when instantaneous rates are measured. Now, in the lab this week, you're not actually going to measure the instantaneous rate. You're going to measure the overall rate of reaction based upon how long it takes the reaction to reach its endpoint. But we could back correlate that value to find the initial reaction rate. But the way that you use the method of initial rates is you do a series of experiments. And in that series of experiments, you start to tinker with the different reactants and play with the different quantities in terms of how much concentration do I have and how fast does the reaction go. And what it allows you to do is it allows you to ultimately isolate reaction runs and compare them directly. So if I compare reaction 1 and reaction 2 here, I can see that my boron trifluoride is held constant, but my ammonia concentration has been cut in half. And when the ammonia concentration is cut in half, I see that the initial rate has been cut in half as well. My net conclusion here would be that ammonia is first order. Why is it first order? Well, when everything else was held constant and I cut the ammonia concentration down, the rate was cut down by the exact same number, by the exact same rate. And that linear relationship is evidence of a first order relationship. And similarly, I could look at reaction 4 and reaction 5 here. Here I'm holding ammonia constant. I've cut the concentration of boron trifluoride in half, and you can see that the rate of reaction has been cut in half as well. We would conclude that since that relationship is linear, that the boron trifluoride is also first order. And from these data, we can ultimately determine the rate of reaction is equal to the rate constant multiplied by the concentration of ammonia to the first power multiplied by the concentration of boron trifluoride, also to the first power. And we also say that the reaction is second order overall, since the orders 1 and 1 would equal out to 2 overall. So that's what the method of initial rates is all about. And again, in your lab, we will talk more about this specifically because the peroxide lab that we are doing is something called the iodine clock reaction. And in that reaction, basically, we're going to manipulate a bunch of variables, not only peroxide concentration and iodide concentration, but also things like acid concentration or so acid concentration or temperature, and looking at all of these different things, how do they change, and comparing the rates directly by comparing how long does each reaction take. So that's kind of where we're going. That's what we're looking at ultimately in that set. Now, the other kind of technique that can be used to find the rate law is something called the integrated rate law. And in the integrated rate law, what you are ending up doing is you are going to plot a graph where we have on one axis the concentration of a substance, usually one of the reactants, and time in seconds or minutes or however long in another one. And what we are looking for here is a plot of the relationship between those two, whether it's curvilinear or exponential or linear. And in particular, we're really interested in the linear relationship because linear relationships are very easy to manipulate from an algebraic standpoint. So when the reaction that we are interested in gives us a straight line, and the axes for that graph are just the concentration of the substance versus time, then we know that that particular reactant is zero order. The equation of the line in slope-intercept form is just like that, where Y is the concentration of the reactant at any moment in time. M is the opposite of the rate constant. T is the time itself. And the y-intercept here is our initial concentration of the reactant. So when we get this kind of a graph for our reactant concentration over time, we know that that reactant is zero order. But more often than not, that's not the case. So how can we manipulate these variables to show us the other ways? Now, the good thing is we don't have to manipulate the time at all. We just really have to manipulate that y-axis. And so if we change the y-axis from the concentration of A to the natural log of the concentration of A and get a linear plot that way, we know it is first order. And the relationship, again, it gets a little bit more complicated, a little bit more complex. I actually prefer a different form of this equation so that you can get the slope-intercept form more precisely. And I'll show it to you here. If you do it this way, natural log of a t is equal to negative kt plus natural log of a at time 0, we see that we fall into the same slope-intercept form that we had in the previous. And so that's what happens if it is first order. If it is second order, things have to change a little bit here. First thing that we should notice is that the slope of the line, because we have essentially inverted the fraction, is going to be positive in this case. The other thing that we should notice is that the y-axis is now equal to 1 over the concentration of A, as opposed to the natural log or just the concentration itself. So we are taking the reciprocal of the concentration. And so as a result of flipping that fraction, instead of the slope being negative and decreasing, the slope is going to be increasing as that concentration gets smaller and smaller and smaller. But it lines up exactly the same way. Y for 1 over A, K for the slope, T for X, 1 over the initial concentration for B. And again, it's always about that linearity. So the real trick for us is finding that line that is the most linear. So if we're doing the experiment in the lab, we're going to really be scrutinizing those R squared values to see which gives us the most linear plot. And that's essentially what these graphs are showing here. So this is a classic first order plot for the CH3C NC and its decomposition over time. And then this is the plot for the decomposition of nitrogen dioxide as it reacts. It's, I guess, not a decomposition, but as it reacts to make N2O4, its reaction is actually second order in nature. Now, before we put this away fully, there is one other concept that I want to share with you, and it's important because it relates directly to the overall concept of the method of integrated rates. It's called pseudo-order kinetics. Now, in pseudo-order kinetics, what we are doing is this is a deliberate technique that is used by chemists to help us to isolate one of our reactants against another. So the premise is this. When two or more reactants are responsible for the rate law / the rate of reaction, we essentially take however many extra reactants there are, amp up their concentrations to a high degree so that they become constant. So we isolate one of the reactants by making its concentration considerably smaller than the rest. The purpose of this is isolation. The reactants in heavy excess do not change in concentration and can be considered part of the rate constant for that reason. So what this means in terms of our rate law, let's just say, for example, we had two reactants. Let's keep it real simple. So our rate law would be R is equal to the rate constant K multiplied by our concentration of A raised to its power multiplied by the concentration of B raised to its power. Now, if we construct a scenario where we make B incredibly concentrated, so much more concentrated than A, that effectively makes the concentration of B a constant. And so we can rewrite this rate law as R is equal to KP. The P there standing for pseudo times the concentration of A to whatever its reaction order is. And the value of the pseudo-order reactant rate constant Kp is equal to the true value of the rate constant K multiplied by the concentration of B raised to whatever power it has. So again, the reason we do this is when we are doing experimental work, it can be very difficult to go between one and the other. And if both are changing or both are capable of changing, then it can be very difficult to track the impact of one versus the other. But by doing pseudo-order kinetics, again, the terminology pseudo there means kind of faked or some kind of implied version. By basically making B a constant for the purposes of this particular experiment, we can isolate A, figure out what A is, and then we can either reverse the process, do a second pseudo-order relationship where we isolate B by flooding it with A, or we can do a secondary experiment where we deliberately change the concentration of B and see how the increased concentration of B affects the rate constant, and then compare the two. So I bring this up because this is featured in the simulation, and pseudo-order kinetics is going to be featured in the lab that you do the following week when we do a kinetics of crystal violet dye lab in person. So tuck this away. This is going to be an important note, something that you're going to want to kind of have at the ready. So let's go back and look at the pre-lab assignments for this week. And let's start with the kinetics of the dye. So based on the information that I gave you, you should be able to answer all of the questions in this pre-lab now. The rate law for the reaction is rate is equal to 0.58 per molar per second times the concentration of A squared times the concentration of B to the first power. You should recognize that 0.58, this is the rate constant, and that these are the orders of the reaction. And because these are the orders, you should be able to figure out what happens to the rate as A is doubled or B is doubled. So that one's pretty straightforward. For the pre-lab in the in-person lab, there is a combination of things going on here. So you do have to look at a couple of these things. So number one, this is just a straight up titration equation. You're going to have to go into the discussion and find the relationship between ultimately the peroxide and the sodium thiosulfate. I will give you a hint. These two equations can be added together. And if you add them together, the iodine goes away, the iodide goes away. And you can see that there is a direct relationship between the hydrogen peroxide and the thiosulfate ion. So that should help you to solve the titration equation there in number one. In number two and number three, again, you're talking about rate law kinds of questions specifically. For number four, you are going to need an equation again out of the discussion here. The equation that you're going to want to use is this one here at the bottom. The rate of reaction is equal to 1/2 times the volume times the molarity of the thiosulfate. So this is 1/2 times volume of thiosulfate multiplied by molarity of thiosulfate divided by the total And then all of that is divided by the change in time. So it's a little bit confusing there. It's important for you to recognize how that equation is set up. But really all that you need to do is just kind of plug in all of the values, and you should be able to get number 4 there pretty easily. Number 5 is a straight up dilution equation question. You should know that one by heart by now. C1 times V1 is equal to C2 times V2. And the last question there, why is this called a clock reaction? Primary reason why is we are looking at a definitive change that is going to occur. The reaction that is going to happen, basically we go from a colorless solution to a bluish black solution almost instantaneously when the reaction has finished. And so we are going to be measuring this reaction rate based upon how long it takes to do that. That is why it is called a clock reaction. It is a timing-based reaction that exists between when we combine everything together all the way up until that color change occurs. And so the rate of reaction for each of those different reaction runs that we're going to do is wholly dependent upon what concentrations of which reactants are present at any given time. So that concludes for us this pre-lab video. If you have any questions, please feel free to reach out to me. Otherwise, I will see you in lab. Have a great day.